Okay, so I decided to broaden the scope of my talk from what I had in the original program. So I'll talk about generic interferometric probes of interesting many-body phases in systems of cold atoms. And this work has been done with several people, especially I want to emphasize the role of Sarang and Michael, who are postdocs, Howard and Kartak, who is a graduate student. So they did the main part of this work. Since many people probably don't have very good idea of what is ultracold atoms, let me give you some idea of what do we mean when we say cold. So of course, one idea is that it's the temperature in Boston, during winter. So people outside of Boston, say from California, it really gets that bad. But actually, that's not what experiments, the temperature which characterizes experiments with ultracold atoms. In fact, the first BEC experiments were done on the scales of microkelvin. And experiments that I'll be presenting today are done actually on scales of picokelvin. So you can see it's quite far from kind of even cold temperatures that we're used to when we talk about superconductors, liquid helium. But obviously, what lies, what really motivates us to look into the system is this idea of universality of physics. And I think this was demonstrated most strikingly in the story with the Higgs particle. So a couple of years ago, we all know about the announcement at LHC when the proton scattering, they saw this peak, which was the Higgs excitation. And actually, within just 1 week of the LHC press conference, there was a paper published by the Max Planck group where they measured the Higgs excitation in the superfluid state of bosons and optical lattices. And what I find particularly interesting is that in order to see Higgs excitation in LHC, experiments were done at energy scales which were 12 orders of magnitude larger than room temperature. And experiments in Munich were done at temperatures which are 12 orders of magnitude smaller than room temperature. So we have 24 orders of magnitude difference in energy scales, but it's really the same underlying physics. And in fact, what is also appealing is that we have a large degree of tunability, say the energy of the Higgs resonance can be continuously tuned to 0. So this is obviously what motivated this whole idea of thinking of ultracold atoms as quantum simulators, sort of like if one can use wind tunnels to study properties of airflow in order to understand what happens around for real airplanes. And that was particularly interesting when people tried to connect, say, the physics of high-temperature superconductors to fermions in optical lattices. But there is a big difference. So we shouldn't think that we can just directly translate everything we know from condensed matter to cold atoms. We really have cold atoms are really independent many-body system. It has its own peculiarities, it has its own characters. Specifically, one of the major challenges is one needs to come up with probes which use toolbox of atomic physics to characterize even familiar phases with phases which we think we know from our solid-state physics experience. And today, I'll focus on just one specific class of experiments, and this is basically interferometric probes. And let me just, again, for people outside of this field, give you a rough idea, like which specific interferometric probe I will have in mind. It's actually one of the kind of basic experiments in atomic physics. So think of a two-level system. It can be, ground and excited state of an electron. It can be two hyperfine states of an atom. Now we make what's known as pi-half rotation. So prepare systems, say, with spin down, and then we make a superposition of spin up and spin down states. And then we let the system evolve. So spin up and spin down states have generically different energies, so maybe even described by different Hamiltonians. So these two states of atom will acquire different phase factors. We can also think about a vector in a Bloch sphere doing precession in the plane, right? So the xy component of the spin is rotating. And then we can apply another pi-half pulse, which converts this phase in the plane into a z, which can be measured. So this tool, this Ramsey interferometry, is really what makes atomic physics so powerful. So that's what underlies atomic clocks, all kinds of sensors, magnetometers, gravitometers. And what I'll be talking today is actually application of the simple idea to measure interesting states of matter. And in the first case, this will be a probe of topological states of matter. In the other case, it will be a probe of a very interesting state, which is a result of competition of interaction and disorder, so-called many-body localized phase. Okay, so let me start by, by talking about interference as a probe of topology, and I'll start with sort of the simplest topological band structure. So this is a so-called Schiffer-Higger model. So this is a one-dimensional model in which tunneling is modulated in space. So it's a model in which we have two sides per unit cell. So if we write Hamiltonian in momentum space, it's 2 by 2 matrix. And we can figure out symmetries of the Hamiltonian, which I'm sure even people in this room know. So, and what we know from general classification is that this Hamiltonian is characterized by an integer quantum number. So I will, again, for people with perhaps more physics background, I'll just give a simple physical illustration where this number comes from. So if we think about A and B sublattices in a unit cell, then our Hamiltonian only contains terms which connect between A and B sublattices. So when we write it a 2 by 2 matrix, it can only have X and Y components of the Pauli matrix, because this is sigma z only has diagonal elements. So therefore, the Hamiltonian can be represented for each value of k as really a vector in the xy plane. And then as we go around the Brillouin zone, so this vector can either make a loop which doesn't go around 0 or a loop that goes around 0, and they cannot be contracted continuously into each other, because when they cross 0, we close the gap. Now, okay, so how do you realize SSH model with bichromatic lattice in optical lattices? So the answer is, well, these are bichromatic lattices, basically lattices in which you have two wavelengths with one has a period of twice the other. We can see that here, let's say the potential is adapt, so we have a high barrier. Here we only have potential from the blue laser, so it's a lower barrier. So clearly it's a system where we have a modulation of tunneling, which in fact we can control by simply changing laser intensity. And now we can ask, well, what's the physical consequence of these topological phases that we want to measure? Well, as was discussed in this conference, it's really kind of all the topological information is encoded in the Berry phase, the phase which we get if we go around the Brillouin zone. So in this case, basically what we have to do, we have to take linear functions and integrate over the Brillouin zone, and then the two states, the two classes will be characterized by the phase difference of pi. Okay, so how does one do this in experiments with cold atoms? Again, it's basically this Ramsey interference. Think about, so these are our two bands of the SSH potential. Prepare atoms at the bottom of the band. Pi half pulse gives a superposition of up and down atoms. Then we apply gradient of magnetic field. Atoms start moving in the opposite direction in momentum space. So this is so-called Bloch oscillations. They seem to separate in momentum space, but actually when they reach the end, the edge of the Brillouin zone, they meet again, because this is really the same point, right? So points are really identified modulo 2 pi. So what we want to do, we just want to measure the phase difference accumulated by spin up and spin down atoms, and it has contribution from the Berry phase, dynamical phase, and Zeeman phase. And obviously, the dispersion is symmetric, therefore dynamical phase should vanish, while Zeeman phase is just the energy difference between up and down. So if you know your magnetic field, you should know your Zeeman energy. So what you expect to measure is, well, for the right configuration, you should see the Berry phase of pi. And life would be so simple, except that when our friends from the Max Planck started doing this experiment, they came back to us and said, well, you know, there is a problem. There is subway in München, and so when a train runs, it changes magnetic field. So from shot to shot, we get completely random magnetic field. So information that we get in these experiments is completely useless. But in fact, this shot-to-shot fluctuations of magnetic field is something that's well known in NMR, and there is a technique to deal with this, which is known as spin echo. So the kind of improved protocol is like this. We start with, again, having atoms at the bottom. We do pi-half rotation to give a superposition, move atoms to the edge of the Brillouin zone. But then, actually, so we do the pi pulse. We basically turn spin-up particles into the spin-down particles. So red to blue and blue to red. Right. Well, and actually, what if we only do that, then atoms would start moving in the opposite direction. That wouldn't help us much. But what one can do, one can actually instantaneously change the lattice from one dimerization to the other dimerization. So when atoms come back, they basically come back in the other lattice. So there is like an extra, somewhat of a complication that in principle, atoms go to the upper band, but again, various phases are kind of the same in the lower and upper band because states have to be orthogonal, so that turns out to be unimportant. So lo and behold, so in this experiment with both this kind of spin echo and swapping of dimerization, one should expect a phase of pi. So this is how the actual experiments look like. So you can see a Bloch oscillation in up and down particles. You see atoms just moving in momentum space, and they reach the end of the Brillouin zone, and they appear on the other side of the Brillouin zone. Then there was a pi pulse, which changes the spin. Atoms start moving in the opposite direction. So this was without swapping of dimerization. This was just simple spin echo. This is with kind of swapping, which, as we said, maps moves atoms to the upper band. And one can compare the phase difference between the two, and we get pi. So this is the kind of direct interferometric measurement of the Zach phase. It's direct measurement of topology of the band structure. And this technique can obviously be extended to higher dimensions. So for example, let me again give you just one example in 2 dimensions. If we take a famous graphene lattice, so it has Dirac points, and these Dirac points have this important property that if we integrate the Berry connection around the Dirac point, we also get pi. It's a very important pi. This explains, for example, why in the quantum Hall plateaus for graphene, plateaus are shifted by 1/2. And so we want to go around the Dirac point and measure this pi. And that's precisely what was done in recent experiments, again, by the Max Planck group. So you can see that the technique is basically the same. They start by preparing this up-down superposition. Then they use gravity to make atoms with both spins move in the same direction and magnetic field gradient to make them move in the opposite direction. So they separate, and then they recombine in momentum space. And then they close around the sequence just to measure the relative phase. And they can actually vary the final point, and it can be sort of the final point which is before, so that the contour does not enclose the Dirac point, or it encloses the Dirac point, and you see that this Berry phase actually, the phase which is measured by this interferometer changes by pi. When they enclose 2 Dirac points, it goes to 2 pi, but 2 pi is the same as 0. So you see this kind of again, the change of interferometric phase that you expect. So this is kind of ideas, theoretical ideas that have already been measured. There are other ideas. This interferometric technique can be extended to more complicated topological band structures, such as, let's say, Z2 band structures, when you have 2 bands. In this case, it turns out that one needs to employ not just Bloch oscillations, but really also sort of, in order to measure this time reversal polarizations, make transitions between the band, which can be done using oscillations at the right frequency. So again, there is a technique for doing this. Okay, I'll skip this because of the lack of time. And there are actually interesting ideas for how this interferometry, where you really measure topology of the many Bedi wave functions, can probably be implemented with cold atoms. So before I sort of finish my review of topology, of studying topological states with synthetic matter, let me point out that it's being done not only with cold atoms, but also with photons. Just show examples, which of course I liked. So one was using quantum walk, where we basically use polarization of lattice to internal states. And this is sort of like some stroboscopic implementation of the Flaquet periodic Hamiltonian. one was able to demonstrate H states for SSH type Hamiltonians, or even H states, which arise from really non-trivial Flaquet evolution operators. Also, quantum Hall-like systems have been implemented with photons. So this is a demonstration of the H state measured experimentally by the JQI group. And in fact, there are also suggestions that these H states should make very useful applications, namely, say, optical delay lines with small losses. Okay, but I want to move on from discussing interferometry as a probe of topological states to talk about interferometry as a probe of many-body localization. And so here, as I'm sure all of you know, there is the kind of motivation for looking into the systems is a question, very difficult question of the interplay of interactions and disorder. So typical statistical physics tells us that systems, if they interacting, they're really ergodic, that, you know, if you make some non-equilibrium state on some microscopic scale, it just equilibrates, it thermalizes, so kind of thermal averaging is the same as ensemble averaging. But we know that this is not always the case, so there is an obvious example. Well, actually, it's now non-interacting system. It's Anderson localization, where, let's say, in one dimension, as soon as we have disorder, even if it's weak, all the single particle wave functions are localized. And if you make some kind of initial state, you basically project them to initial wave functions, and the system is stuck. It cannot really relax. The important question is, of course, what will interactions do to this state? And originally, people thought, oh, any interactions may be sufficient to make the system ergodic, but sort of starting with Anderson, and then more recently, these two papers are really motivated, sort of more careful look at this problem. There was a suggestion that if the system is isolated, in fact, it cannot act as its own path, right? So therefore, this kind of an anergodic nature of the system with disorder will stay. And particularly clear example was given by David Hughes and Arijit, where they looked at Heisenberg model with random magnetic field. They prepared the system with inhomogeneous magnetization and just looked at the fraction of magnetization which relaxed after a long time. So you can see this is sort of the scale of random field. And so if the random field is small, then basically everything relaxed, but as random magnetic field gets larger and larger, basically magnetization stopped relaxing. So that's why the system is really stuck in a non-equilibrium state. But obviously, if many-body localization was the same as single particle localization, that would be really boring. Well, but it's actually, again, it's different. And this was the really pioneering work was done by Joel Moore and collaborators, who pointed out that there is something very special about the many-body localized phase. And what they did was to take, again, random XXZ models. They prepared it in a factorizable state and then let it evolve and looked at entanglement entropy as a function of time. And okay, if they take a system which is essentially non-interacting, this is when Z component is 0, okay, they see that entanglement entropy growth and then saturates. But if there are interactions, it actually continues to grow in a very peculiar logarithmic fashion. So somehow, even though the the system is localized, it's not ergodic, yet there is some kind of growth of entanglement over longer and longer length scale. And so several papers actually came up with a simple cartoon picture of what's happening, that even if the system is localized, one can still think of essentially two-level system which have kind of exponentially weak interactions with each other. And so even if they start being not entangled, then after the time, now it's exponentially long time, they do become entangled. And therefore, of course, if we take log, we will see that the entanglement entropy, sort of the number of pairs which really get entangled, really goes as log of the time. And so these systems with both disorder and interactions can be very natural for cold atoms. I just give you a few examples. So this is, for example, cold atoms with random potential created by speckles. There was an interesting realization in GLA when they have sparsely populated optical lattices, and angular momentum of molecules is like a spin Then there are Rydberg atoms, where basically when Rydberg atoms are created, they're created in random positions. Or there are atom-like systems, say NV centers and diamond. So what we want to do is actually come up with an experiment, with an ideal experiment that can really give us smoking gun signature of this many-body phase, of this many-body localized phase. And okay, so I'll skip like one interesting aspect. So effectively, this many-body localized phase are integrable systems. So you can schematically think about them as a state in which you have pairs of strongly interacting spins which are rapidly precessing around each other, and they kind of separate as integrals of motion. And you have this hierarchical construction. Let's say these spins, two spins are strongly coupled. Then to mediate this long-range interaction, one needs to virtually break this pair of spins. So, and then one can entangle these two spins and so on. So, but these kind of spins which are kind of processing quickly around each other and they're weakly coupled to the rest of the system can be thought of as integrals of motion. And this is something that will be useful to us later on. Okay, so now how do we want to probe many-body localization? Well, again, it's actually this Ramsey protocol. So the only new feature is that in these systems, one can do it in a local fashion. One can apply, we have a many-body spin system. One can apply a local pi-half rotation, let the system evolve, and then measure locally. Well, in fact, often measurements can be done globally because when you measure, you annihilate the system. But for our purposes, let me just think about, pi-half on one spin evolution, then pi-half and measurement on the same spin. So one can show that under fairly general assumptions, okay, sorry, this should be interchanged. This Ramsey interference is nothing but the measurement of the usual spin correlation function, but in time rather than in space, in frequency. So typically in condensed matter, we talk about measurements in frequency domain, whereas here, this Ramsey protocol really measures this correlation, retarded correlation function in spin, in time. Now, well, what can we learn from the spin correlation function? Well, let me show you one trick how that helps to think about this. Let's just take, okay, one part of the correlation function. So it's a spin operator at time t, spin operator at time 0. Well, we know, so to get spin operator at time t, I just need to dress it by Heisenberg evolution. But now let me flip this expression around and actually say that now what I have is a Hamiltonian evolution operator sandwiched between two spin operators. But spin operators actually really changes the sign. Can be it's really like a pi rotation around the x-axis, so it changes the y and z components of the spin. Therefore, I can alternatively think about this whole expression as kind of evolution forward with a Hamiltonian, which is different from my initial Hamiltonian, just that the spin components on one side, y and z components, have changed sign, so it's slightly different Hamiltonian. And then I take an overlap with an initial state, right, and that evolved back with it's an eigenstate of this initial Hamiltonian. Well, and so how does it help us to understand what these correlation functions will look like? Well, if the system is strongly localized, you expect that if you change the Hamiltonian locally, you only make a superposition with a few eigenstates. Therefore, this evolution operator will really just have a few oscillations at a few frequencies. Whereas if the system is delocalized, we will actually get a decay. Right? So it's like a finality catastrophe. Introduce a local potential, we generate a lot of excitations which just fly off to infinity. So we would say, oh, perhaps that's the smoking gun of localized versus non-localized. But obviously the problem is that, okay, the frequency of these oscillations depend on the eigenstate which you are using. So if we talk about high energy states, we really have to average over a whole bunch of oscillations. And if we average over them, we get a decay. One can analyze this decay quantitatively. Let's say there was interesting work by Joel on this, but what I'm interested in is something which is more qualitative, something more striking. So can we really distinguish this kind of behavior if something's truly localized from something which is delocalized and we're just seeing, so this is just a result of averaging over many oscillations, whereas this is a true decay. Well, okay, so there is one kind of super simplified picture. Let's take single particle localized regime. So that's where I really just have random magnetic field coupled to the spin. So now, if from shot to shot my magnetic field changes, and so like for a given configuration of magnetic field, I would get a certain oscillations, but if from shot to shot I have different frequency, I would obviously get a decay, but I want to see that it's really, what underlies this decay is really oscillations, which just fluctuate from shot to shot. What I can do a spin echo, right? I can change my h to minus h, which I can do by simply rotating, applying a pi pulse in the middle of my evolution, so that the system basically evolves half of the time with this Hamiltonian and half of the time with the Hamiltonian in which I reversed the sign of the magnetic field. And then if I look at what happens at the end of the evolution, if I have the single particle localization, there should be no decay. So, okay, well, we should use spin echo. So clearly this can help us to distinguish localized phases from delocalized diffusive phases, but that clearly is not the full story, because it doesn't help us to separate single particle localization from anybody localization. So in order to distinguish two types of localization, we have to do something more elegant. And this is basically, again, borrowing idea from NMR. It's the idea of so-called DIO, double electron-electron resonance. So basically, in the single particle localization, okay, this spin doesn't know about what's happening beyond localization length. Like all the spins are decoupled. Whereas in the many-body localized phase, we know that spins are still coupled to each other. There's exponentially weak but finite interactions. So we can actually mess up the perfect revival of the spin when we do spin echo by messing up spins far away. So we have to modify our simple spin echo protocol to actually do something that messes up a spin in region 2, which is a certain distance away from the spin we're really probing. Then for single particle localization, this should not do anything. And for many-body localized phase, this should lead to the addition of decay. And okay, so the model, so this was kind of like, you can say wishful thinking. Okay, well, we hope that it will look like this, but we have to study some concrete model. So the model that we looked at is really, again, this Heisenberg model with random magnetic field. And what's useful about this model, as I said, is that by changing JZ, we can tune it between non-interacting regime and interacting. When JZ is 0, it's just a model of non-interacting fermions. When JZ is finite, it's truly interacting system. And now, okay, on this model, if you do simple spin echo, so this, I believe, is when JZ is equal to 1, so it's interacting system, like strongly localized. And in fact, you see precisely what we kind of conjectured, that if I do simple spin echo, it prevents me, kind of my signal, the coherent, this kind of Ramsey fringes, amplitude of Ramsey fringe from decay. I revive my full amplitude of the transverse spin. If, on the other hand, I mess up a spin a certain distance away, I can see that with time, this amplitude of Ramsey fringes decays. And in fact, one can also see that this is a property of interacting system, because now one can systematically change JZ. So this is this DIO protocol. When JZ is equal to 0, even adding this DIO part, like messing up spins in region 2, actually doesn't prevent full revival, whereas as we increase JZ, the revival gets suppressed more and more. And in fact, the suppression is of a very specific power law fashion. And so here you can see, so if we change the distance between region 2 and 1, it only changes the time at which the suppression occurs, but the exponent really depends only on the localization length. And so here it is a kind of a cartoon argument of how this happens. So think about kind of, again, it's, as we said, kind of many-body localized phase is like an integrable system. So in the simplest case, I can think about it as spin a half, which is just coupled by, so they have random magnetic field and they have this tau z interaction. Clearly, there is infinite number of conservation laws, right? So because tau z on each side is an integral of motion of this Hamiltonian, and this j, ij decay exponentially. So now, if we just think about this protocol, so we're interrogating one spin, let's say call spin 1, and so its frequency, and we're asking, again, basically, that this DIO protocol, we will get a kind of a decay of Ramsey fringes when this spin that we interrogate gets mixed up with a spin which is a certain distance away. And spins, okay, get mixed up, they get into entangled state due to this interaction. And you can basically argue that, like, if we think about spin 1 and all the other spins, we can divide them into pairs, and for any given time, these pairs either had time to entangle with each other if this JT is greater than 1, or they did not have time to get entangled if JT is less than 1. And we know that for every entangled pair, the amplitude of Ramsey fringes basically goes down by a factor of 1/2. And so we have to take 1/2 to the power of the number of these spins which got entangled, and that goes as log of t. And therefore, this decay of Ramsey fringes should occur with the exponent, which actually is determined by localization length. And that's precisely what, let's say, one can test just by changing disorder, changing the localization length. One can see this exponent changing. Okay, so my time is up, so I'll stop here, and I hope I gave you a taste how one can use these new interferometric probes not only to do kind of bread and butter atomic physics, spectroscopy and metrology, but also probe interesting kind of solid state-like states, either topological or, in this case, many-body localized states. Thank you.
So in the first part of your talk, I think you mentioned you can mirror the Berry phase in the topological state. So do you think you can mirror the Z2 index or the Z2 topological order? You know?
Yes, you can. That was the paper that we wrote.
Okay, I see. Yeah, I see. Okay. Any others?
So for the second part of the talk, one of the big questions, I guess, about MDL is being able to show that there's no energy transport. Is there an experiment that's feasible with atoms to look for that?
Well, but in some sense, so you know that there is no magnetization transfer. But
yeah, easier to prove either numerically or, yeah. But as you know, again, there's one proof by Embry of a model that doesn't probably have even energy transport. That one doesn't have U1. I guess I can see how the experiment would work for magnetization transport, but one might worry that, yeah, particles are localized, but energy is not. I mean, maybe that's artificial, but I guess there are people.
well, so in this specific measurement, I guess what you would like to measure, you can separately measure, let's say, magnetization, which is the Zeeman part of the energy, and then you want to measure the exchange part of the energy. So yes, so this actually is possible to measure because, again, early experiments demonstrated that you can really measure, like, for given two spins, whether they make a singlet or a triplet state. So, I mean, that was done in models without disorder, but okay, with the slope addressability, the same techniques can be done. If it's singlet or triplet, you can, again, using super lattices, bring them to specific configuration.
I was going to say, but you have a complication because with a homogeneous system, it would be one thing. So you can measure the correlations and immediately nearest neighbor correlation will give you the energy. But if there's also a coefficient that's varying from one place to another, I'm not sure whether you
Actually,
this will allow.
Right, so I guess if you can make reproducibly disorder, if you can at least show that in the same disorder your kind of spin configuration has kind of the ratio of singlets to triplets doesn't change, so yes. But if you, and that depends on the system, say in some systems you can make the same disorder, in other systems you cannot. So for example, this other probe which I advocated is robust so that even if from shot to shot my disorder changes, that will still be robust. But for this one, yeah, I will probably need to work with the same configuration of disorder.
Any more questions? Yeah, if not, let's thank Eugene and Sophia for the. Yeah, let's come back at 3:15.
Yes.
Actually, very nice. I do have a simple question. Maybe
Sure.
you compare this spin echo and